Hello and welcome to the Maths 2 component of the online degree on data science. In this video, we are going to talk about linear transformations and their relation with ordered bases and matrices. So, this is continuing on our previous video where we have defined linear transformations. We have already seen the connection, a little bit of connection between bases and matrices with linear transformations, and we are going to expand on that in this video. So, let us recall first what we have done so far. We have studied what is a linear transformation. So, linear transformation was a function between two vector spaces. So, a function f from v to w, let us say, which satisfies linearity. So, linearity is the condition that f of v1 plus c v2 is f of v1 plus c times f of v2. Equivalently, we could write it as two separate conditions. F of v1 plus v2 is f of v1 plus f of v2, and f of c times v1 is c times f of v1. And you can use this to say that f of summation ci vi is summation ci f of vi. In other words, the sum comes out and the scalars come out. Okay, that is a linear transformation. We have seen what is an isomorphism of vector spaces, namely if you have a linear transformation which is a bijection, that is what we call an isomorphism of vector spaces. And finally, we saw in the previous video that a linear transformation is determined by the values it takes on basis vectors. Equivalently, or rather conversely, if you have a set of values, a set of vectors in the codomain W and you define a function on the basis given by f of vi is wi, you can extend this function to a linear transformation f v to w, and we explicitly wrote down how to extend it. Okay, so, extending maps on basis to linear transformations. Fine. So, let us continue from this point and study first a very important property of finite dimensional vector spaces. So, let V be a vector space with dimension n, choose a basis v1, v2, vn, and we are going to define a function f from v to rn, okay, which sends vi to ei. Okay. So, how do we do that? Well, we define the map f of vi equals ei. This is only on the basis v1, v2, vn. So, it is a map on the set v1, v2, vn, and then we extend it to a linear transformation, which by abuse of notation we are going to still call f, and of course, as a result it continues to take vi to ei. So, the claim is that V is an f is an isomorphism. Let us check why that is the case. So, first let us write down what is the function. So, if you have V is summation ci times vi, then f of v is defined as summation ci times ei, right. And we saw as soon as you do this that from here we obtain that f of vi is equal to vi. Excuse me. Now, why is this a isomorphism? We have seen already that this is the linear transformation given by extension. Yeah, so it is a linear transformation. I did not check that in the previous video, but I hope that you have checked it. If not, you should do it right now or when you finish this video. Okay. So, f of v is summation ci ei and f of vi is ei. So, let us check that this is an isomorphism. To check that, we have to check it is on 1 and on 2. So, how do we check on 2? So, it is on 2. How do we check that? Well, let us take a element of Rn. Let us say I have x1, x2, xn. Let v equals summation xi vi. So, the ci is xi. So, this is an Rn. Okay, then what is f of v? F of v is summation xi ei, which is exactly in terms of as a column vector, this is the column vector x1, x2, xn, right. And here when we say we are going to write it as a row vector, f of v is the row vector corresponding to this. So, f of v is exactly x1, x2, xn. Yeah. So, this means it is on 2. So therefore it is onto. Okay, I have checked that it is onto. Now let us check 1 1. It's a linear transformation, so it's enough for me to check that f of v 0 implies v 0. But what does it mean to say that f of v 0? First of all, what is 0 in Rn? It's the origin or the vector 0 0 0. So let's put in the definition of put in the definition of f of v, which is written above. So f of v is summation ci ei. This is 0 0 0. But what is this summation ci ei? So v is written as summation ci vi. Yeah, these are those, the ci's are those coefficients, right, coming out of the unique way of writing v as summation ci vi, where I of course runs from 1 through n. Okay. But on the other hand, this is the column vector C1 C2 Cn, as we have been consistently doing. I am abusing notation between rows and columns because here there is no matrix multiplication. So in other words, this is C1 C2 Cn, but this is 0 0 0. That means each of the ci's is 0. But what does that? So for all I, but that means v is equal to 0 times v1 plus 0 times v2 plus 0 times vn. So these are all the scalar 0, which evaluates to the vector 0 in your vector space v. So I have proved that it is 1 1. Okay, that's why it's an isomorphism. Okay, so last video we didn't see any examples of linear transformations which are not linear mappings. All of them were on Rn and Rm and so on. So this is our first example where we are going to study a linear transformation. So let us look at this subspace W of R3, which is given by x, y, z, where x plus y plus z is 0. We have checked in a previous video that this is indeed a subspace. This was the null space of something. I will leave that part to you to recall where we did this earlier. So this is a subspace of R3. So in particular, which means it's a vector space in its own right, by which we mean that if you take two elements of the form x, y, z such that x plus y plus z is 0, then they add up and you get a new vector which is also satisfying the same relation, that x plus y plus z is 0. And if you take a scalar multiple, the same thing happens. Okay. So we had worked out earlier that a basis for this subspace is -1 1 0 and -1 0 1. You should check this. Okay, so the homomorphism f obtained by extending f of -1 1 0 is 1 0 and f of -1 0 1 is 0 1 is an isomorphism. Why is that? That's because if you write any x y z in W, it can be uniquely expressed as y times -1 comma 1 comma 0 plus z times -1 comma 0 comma 1. You might wonder why that is the case, because you get minus y minus z in the first coordinate and then y in the second and z in the third coordinate. But minus y minus z is equal to x. Why is that? Because x y z is in W, that means x plus y plus z is 0, that means x is minus y minus z. Okay. So this is fine, and it is unique because this is a basis. Okay. So then we know how to extend functions which are defined on a basis to linear transformations. So you get that f of x y z is y times 1 comma 0 plus z times 0 comma 1, which is y comma z. So this is actually the projection to the yz plane. Okay, this is a projection from W onto the yz plane. I didn't check why it's an isomorphism, but it's clear it's an isomorphism. I'll claim, because let's see onto how. So projection map, it's always going to be onto. So if you want y comma z in R2, so choose x is minus y minus z and consider x y z in W. It does lie in W because x plus y plus z is W, sorry, is 0. So, therefore, f of x y z is this y plus z, is y comma z, right. So, you have to choose x, otherwise we do not know x y z is in W. So, you have to get something which is in W. So, therefore, it is on 2. So, we have checked on 2 and 1 1 is very direct. So, if f of x y z is 0, so what is 0 in R2? It is 0 comma 0, and let us put in the value of f of x y z, it is 0 0 0 0. This means y is 0 and z is 0, but that means that x is 0 because x is minus y minus z, because remember that x y z belongs to W. So, the statement is if f of x y z is 0 for x y z belonging to W, x is minus y minus z, which is 0. So, in other words, x y z is 0. By 0 I mean the 0 vector in W. Okay. So, we have checked it is an isomorphism. So, I should have put a tick mark there. Okay. Let us see how to get the matrix form for a linear transformation. So, first let us do this example. So, we have f of x y is 2x comma y, and it is clear that this is the same if we fudge between rows and columns again by writing 2 0 0 1 times x comma y, x y, the vector x y, the column vector x y, right. So, you get 2x y, which we write as a row vector as 2x comma y. Okay, what is the significance of the coefficients in this matrix? So, if we consider a standard basis 1 0 and 0 1 for R2 and evaluate the function in terms of the basis, we get f of 1 0 is 2 0, but 2 0 can be written as 2 times. So, you write this vector 2 comma 0 in as a unique linear combination of the basis vectors. So, it is 2 comma times 1 comma 0 plus 0 times 0 comma 1, and similarly f of 0 comma 1 is 0 comma 1 is 0 times 1 comma 0 plus 1 times 0 comma 1, and it is clear this 2 0 0 1 that we are getting here is being obtained, those are the numbers obtained in this matrix. Okay. So, we can make this more general. So, let f v to w be a linear transformation. Suppose we have ordered basis for v and w. So, v 1 v 2 v n which we are calling beta is an ordered basis for v. So, what do we mean by ordered basis? We mean that v 1 is indeed the first vector, v 2 is indeed the second vector. So, I want to distinguish between the basis 1 0 0 1 and 0 1 1 0. Yeah, this is the standard basis. I mean, both of these can be thought of as a standard basis, but this is as the standard. So, this is the ordered standard basis, okay, and this is not the ordered standard basis. Okay. So, this is a different ordering for the standard basis. So, as ordered basis they are different. Okay. So, suppose both of these have ordered basis given to us, and so we can write f of v I as a unique linear combination of the w j's. So, you write f of v 1 is a 1 1 w 1 plus a 2 1 w 2 plus a m 1 w m, f of v 2 is a 1 2 w 2 w 1 plus a 2 2 w 2 plus a m 2 w m, and so on. F of v n is a 1 n w 1 plus a 2 n w 2 plus a m n w m. Then so notice I am not, I mean these aij's are written in a particular way. This is more like aji. Okay. Then the matrix corresponding to this linear transformation with respect to these bases, the ordered bases beta and gamma, which were v 1 v 2 v n and w 1 w 2 w m respectively, is given by a 1 1 a 1 2 a 1 n, a 2 1 a 2 2 a 2 n, a m 1 a m 2 a m n. I want to point out that the column here a 1 1 a 2 1 a m n a m 1 were the coefficients occurring in the linear combination which express the vector FV1. The coefficients in the second the entries in the second vector, the second column, are what occurred in the second linear combination for f of V2, and so on. The entries in the nth column are what occurred in the expression for f of Vn. So, keep that in mind. Okay. So, just as an example, if you have V is W is R2 and beta is gamma is 1 0 and 1 1. So, it is not the ordered standard basis, it is this one, and let us say f of x y is 2x comma y. Let us work out what that means. So, you take f of 1 0, that is 2 comma 0, and you express that in terms of your basis. So, as in terms of our basis, this is 2 times 1 comma 0 plus 0 times 1 comma 1, and you take f of 1 1, that is 2 comma 1. So, you express it in terms of our ordered basis. So, this is 1 times 1 comma 0 plus 1 times 1 comma 1. Then the corresponding matrix is the 2 goes here, the 0 goes here, right. So, it is in that the first column, and then this 1 goes here, and then this 1 goes here. Okay. So, that is what this corresponding matrix is. Okay. So, can we recover the linear transformation? Indeed we can, and that is what we are going to study now. Suppose A is an m by n matrix, what is the corresponding linear transformation? So, let V be in V. We express V in terms of the Vj's. So, express V as summation Cj Vj. Define f of V to be summation Cj Aij times Wi. So, here notice that this is slightly different from what we have done before. In our previous thing, what we did was we specified values for f of V1, f of V2, f of Vn, and then we said you can extend this to a linear transformation. Okay. Now, we a priori have not specified what are the values of V1, V2, Vn, meaning what is f evaluated on V1, V2, Vn. Instead, we have specified a ordered basis W1, W2, Wm, and we have specified a matrix A. So, now what we are going to say is f of V is whatever expression we have here, summation Cj times summation Aij Wi. So, you have to check again, this is a linear transformation, not hard. You can write this in terms of in a matrix form, and that will maybe simplify things. But let us evaluate what is f of Vk, right. So, what is f of Vk? So, f of Vk can be obtained by putting Cj to be 1 for j is equal to k, and Cj to be 0 when j is not equal to k, and in that case we get f of Vk is everything disappears in this sum except Ck, which is 1. So, we put j is equal to k. So, you get Aik summation Aik Wi, which is A1k W1 plus A2k W2 plus Amk Wm. So, it is this vector which is f of Vk. So, now we could equivalently have said that we specify the vectors A1k W1 plus A2k W2 plus Amk Wm similarly for the as the kth vector. So, we have a set of n vectors like this as k varies, and these are the n vectors which are the images of Vi's, and now we can say the rest is given by extending this f to a linear transformation. Okay, that's what we are saying here. And how do we identify these vectors? Well, this is exactly what the entries in the kth column. Okay. So, yeah, these are the entries in the kth column. So, the matrix corresponding to f is indeed A, because remember how we get that matrix. To get that matrix, we take the basis V1, V2, Vn, we write f of Vi or Vj in terms of the linear combination of Wi's. So, here this is exactly the coefficients, and those coefficients are exactly what is going to go into the kth column. So, that is exactly what A is, right. So, the matrix corresponding to F is indeed A. So, what have we done here? We saw that for a linear transformation and ordered basis, we can get a matrix A. That was on the previous slide. On this slide, we are saying that suppose we have the ordered basis and the matrix A, can we get a linear transformation so that this is the corresponding matrix, and indeed we can, and this is how we do it. Okay. Okay. So, the point is, this is actually setting up a bijection between linear transformations and matrices. So, if beta and gamma are ordered basis for vector spaces V and W, and n is the dimension of V and m is the dimension of W, there is a bijection, linear transformations from V to W to m by n matrices, of course, over R. How do we get this? So, if I have a linear transformation, I know how to get a matrix A, right, because beta and gamma are specified. So, once I know this, I know how to get A. This was by writing f of V j as summation A I j W I. Right, this was, so the A was the matrices, sorry, the matrix A is the ijth entry is this Aij. I have to apologize because I have messed up my notations here. This is f of f of V j is summation over I and not over j. So, j is fixed, right, j is fixed, summation A I j W I. So, this is what these coefficients are exactly what go into the jth column. Okay, that is how you get your matrix A. On the other side, if you have a matrix A, how do I get my F? That is exactly what we saw on the previous slide. By looking at, so we define f of V j to be summation A I j W I. This time I should put a capital here, A I j W I. What is this capital A I j? This is exactly the ijth entry of this matrix, and then extend to a linear transformation, right. That is what we saw earlier, that we can do that. Okay. So, it is clear that if you start with A, produce F, and then ask what is the corresponding matrix, you get back A. That is what we saw on the previous slide. And if you notice, if you see how we have done this, if you start with F, get your matrix and then get the corresponding linear transformation, then you will clearly get back F. So, I will leave that to check to you that this is indeed a bijection, this is the correspondence. Okay. So, let us do an example, not of the correspondence, but of getting the matrix and so on. So, let W be x y z such that x plus y plus z is 0, we have seen this before, and V is R2. Let beta be the basis that we saw, the same ordered basis that we saw before, and gamma be the standard basis, by which we mean the ordered standard basis. So, we had an isomorphism which was f of minus 1 comma 1 comma 0 was 1 0 and f of minus 1 comma 0 comma 1 was 0 1. This was a projection to the yz plane. So, the matrix corresponding to this linear transformation F with respect to the ordered basis beta and gamma is just 1 0 0 1, the identity matrix. Why is that? How do we get the matrix? You look at F evaluated on the basis vectors and then write that in terms of the basis vectors for the range space. So, in this case f of minus 1 comma 1 comma 0 is 1 times 1 comma 0 plus 0 times 0 comma 1, and similarly minus 1 comma 0 comma 1 is 0 times 1 comma 0 plus 1 times 0 comma 1. And that is how you get your identity matrix. Okay. But now suppose we change our basis. So, instead of taking the standard ordered basis, we take the basis 1 0 and 1 1 on gamma. Okay. So, we have the, remember we have the same linear transformation, but we are changing our ordered basis. Okay. Let us see what happens. So, now if we write f of minus 1 comma 1 comma 0 in terms of the basis ordered basis gamma, we get, so remember that this is 1 comma 0, that is 1 times 1 comma 0 plus 0 times 1 comma 1. So, no change in the coefficients that were coming in the first equation earlier, but for the second one we have f of minus 1 comma 0 comma 1 is 0 comma 1 projection to the yz plane, and 0 comma 1 now can be written as minus 1 times 1 comma 0 plus 1 times 1 comma 1. So, what is the corresponding matrix? The corresponding matrix is, you put these coefficients in the first equation as the first column. So, this is not correct what I have written here in the first column. So, this is 1 and then this is wrong, and what should have been there is 0, and then again here this should have been the minus 1 and the 1. Okay. But the main point here is, in the previous slide we saw that we got the identity matrix with respect to the ordered basis beta and a different basis gamma, the standard ordered basis. Yeah, whereas here we get a different matrix, yeah, when we change the basis. So, your basis, what basis you choose is very important. So, it will not happen that you will change basis and get the same matrix. Yeah, with different ordered basis you will get different matrices. Okay. But if you keep your basis constant, then there is a bijection between linear transformations and matrices. Yeah. So, you will get the same matrix in particular. Okay. So, the important part here is that you will get is that changing ordered basis gives you different matrices corresponding to the same linear transformation. So, it is a good question to ask, if you take a linear transformation, what is a possible set of matrices that you can get, right? And this is something interesting, and we will be looking into that in a video later on. Thank you.